Hello, this is a revision video for AP Chemistry, Chapter 5, Kinetics. As this is a revision video, only the essential information is covered. For more detailed explanations and full video lessons, please check the links in the description below. Good luck revising.
The rate of a reaction refers to how quickly a chemical change occurs. It is usually expressed as the change in concentration of a reactant or product over time, typically with units such as moles per litre per second. So rate equals change in product concentration divided by change in time, or rate equals negative change in reactant concentration divided by change in time. Note the negative sign for the concentration of the reactant because reactant concentration decreases as the reaction proceeds. The balanced chemical equation of a reaction provides the ratio of how quickly each species is used up or produced compared to one another. For example, for the reaction 2NO2 goes to form 2NO plus O2, the rate of NO2 disappearance will equal the rate of NO formation. Because their molar ratios are the same, for every 2 moles of NO2 that decompose, 2 moles of NO are formed. However, the rate of O2 formation will be half the rate of NO formation, because the molar ratio of NO to O2 is 2 to 1, so for every 2 moles of NO that are produced in a given amount of time, only 1 mole of O2 will be produced. There are several factors that affect the rate of a reaction, and these are all covered in more detail in further topics in Chapter 5. However, as a brief overview, temperature, concentration, surface area, and catalysts all affect the rate of a reaction. The higher the temperature of reacting particles, the faster the rate of reaction. The greater the concentration of reactant particles, the faster the rate of reaction. The greater the surface area to volume ratio, the faster the reaction rate. Catalysts also increase the rate of a reaction by providing an alternative reaction pathway with a lower activation energy. These are all covered in more detail in further subtopics in Chapter 5. The type of reactants reacting also have an influence on the reaction rate. For example, reactions involving ions in solution are often very fast. Substances in a liquid and gas phase will often react faster than substances in a solid phase, but there are exceptions to this. A rate law is an expression that relates the rate of a reaction to the concentration of reactants. It is determined experimentally, not from the balanced chemical equation. So, for a general reaction such as A plus B going to form C, the rate law would be rate equals rate constant K multiplied by the concentration of A raised to the order of reaction with respect to A, multiplied by a concentration of B raised to the order of reaction with respect to B. And the overall order of the reaction equals m plus n. The order of reaction with respect to a reactant tells us how the rate changes as the concentration of that reactant changes. In other words, it tells us how the rate of reaction changes when we change the concentration of reactant. If a reaction is zero order with respect to a particular reactant, then changing the concentration has no impact on the rate of reaction. You could double or triple the concentration of reactant, but the reaction rate will stay the same. If a reaction is first order with respect to a particular reactant, if you change the concentration of that reactant, the rate will change by the same factor. So, for example, if you double the concentration of reactant, the rate of reaction will also double. If a reaction is second order with respect to a particular reactant, now if you change the concentration of that reactant, the rate of reaction will change by that factor squared. So if you were to double the concentration of reactant, the rate would quadruple, because 2 squared equals 4. Equally, if you were to triple the concentration of reactant, then the rate would increase by a factor of 9, because 3 squared equals 9. Orders of reaction can be determined using graphs of experimental data. We can measure how the initial reaction rate changes when reactant concentrations are varied. The shapes of these graphs can identify the reaction order for each reactant. We can determine orders of reaction using experimental data by comparing how initial rates of a reaction change when a concentration of reactant is also changed. For example, in the table shown, we can see that for the reaction A plus B going to form C, the reaction is carried out 3 times, each with different concentrations of reactants. In the first experiment, the concentration of A and B are both 0.1 mole per decimeter cubed. However, in the second experiment, the concentration of A has been doubled, but the concentration of B has remained the same. But the rate of reaction has also doubled. This means the reaction must be first order with respect to A, because the concentration of A was doubled and the initial rate of reaction also doubled. First order. Experiments 2 and 3 both have the same concentration of A, but the concentration of B has now been doubled. But the rate of reaction has quadrupled. So the reaction must be second order with respect to B, because the concentration of B has doubled and the initial rate of reaction has quadrupled. 2 squared equals 4. Exam tip here: the order of reaction with respect to a particular reactant isn't connected to the balanced chemical equation. You must use experimental data to determine orders, never just the balanced equation. The rate constant K is a proportionality constant in the rate law. The value of this constant is temperature dependent, and the units reflect the overall reaction order. For example, the units for K for a zero-order reaction overall could be mole per litre per second. For first order, second to the minus 1. For second order, litres per mole per second. Exam tip here: remember, rate constant K is temperature dependent. If the temperature of a reactant system changes, the rate constant K will also change. A graph of concentration against time for a reaction that is zero order with respect to a reactant will be linear with a slope that is minus K, the rate constant. This is because a straight line graph follows a y equals mx plus c function. Well, here y is the concentration of A at a given time t, m, the slope of the line, is minus k, the rate constant, x is t time, and c, the intercept, is the concentration of reactant at the start. Notice here that the units of K will be mole per litre per second. This graph clearly shows us that the rate of reaction is independent of the concentration of A. Because the concentration of A is decreasing at a constant rate, this means it doesn't matter what the concentration of A is, the overall rate of reaction must be remaining constant. So, concentration of A has no impact on rate, means it must be zero order. If a reaction is first order with respect to a reactant, then now a plot of the natural log of the reactant concentration as a function of time will be linear. Again, it's a straight line which will follow y equals mx plus c function, but this time y is the natural log of concentration of A at a given time, m, the slope, is again negative k, the rate constant, x is t time, and c, the intercept, is natural log of concentration of A at the start. This graph shows us that the rate of reaction is dependent on the concentration of A. Because the concentration of A decreases exponentially, the rate at which the concentration of A changes slows down, it decreases. What this really tells us is that the reaction gets slower as the concentration of A decreases, meaning the rate at which concentration of A decreases slows down. One extra small point to note here is that the half-life for a first-order reactant is constant, so the time it takes for the concentration of reactant to decrease to half its original concentration is constant, regardless of the starting concentration. The equation is half-life equals 0.693 divided by rate constant K. We can see this if we plot a simple graph of concentration of reactant against time. The time intervals for the concentration of reactant to half are the same throughout. For second-order reactions, a plot of the reciprocal of the concentration of that reactant against time will give a linear graph with an upward slope. This shows us that the rate depends on the concentration of the reactant squared. Again, the straight line will follow y equals mx plus c function, with y being 1 over concentration of A at time t, m the slope, rate constant k, x being time t, and c the intercept being 1 over concentration of A at the start, which here will be 0. Exam tip here: these graphs can look quite confusing and the maths behind them can be quite intimidating. Just make sure, however, that you can identify the order of reaction with respect to a particular reactant using the shapes of these graphs. So if concentration against time is linear, 0 order. If natural log of concentration against time is linear, first order. And if 1 over concentration versus time is linear, it's second order. And the slope of all of these lines can be used to find the rate constant K. An elementary reaction is a single-step process where reactants form products in one collision. Reactant particles collide together and products get formed. For elementary reactions, the rate law can be written directly using the stoichiometric coefficients from the balanced equation. There are three types of elementary reactions: unimolecular, bimolecular, and termolecular. A unimolecular reaction involves one molecule decomposing to form a product. So, for example, A going to form B would give a rate law as rate equals rate constant K multiplied by the concentration of A, and the reaction would be first order overall. A bimolecular reaction involves two particles colliding to form a product. For example, A plus B forming C would give a rate law of rate equals rate constant K multiplied by the concentration of A multiplied by the concentration of B, and would be second order overall, first order with respect to A and first order with respect to B. A termolecular reaction involves three particles colliding simultaneously. For example, A plus B plus C going to form D. Here, the rate law would be rate equals rate constant K multiplied by the concentration of A multiplied by the concentration of B multiplied by the concentration of C, and the reaction would be third order overall, first order with respect to A, first order with respect to B, and first order with respect to C. Termolecular reactions are incredibly rare because all three particles have to collide at the same time and in the correct orientation and with the correct amount of energy to lead to product formation. Instead, reactions which involve several reactant particles usually proceed through a series of bimolecular steps and are represented using reaction mechanisms which break these complicated reactions down into a sequence of smaller, simpler elementary reactions. Exam tip here: if you're told a step is elementary, then you're allowed to use the balanced reaction equation in the rate law, but never do this for an overall reaction, only if you are told the step is elementary. This is because most reactions actually proceed by several elementary steps, so the overall rate law won't simply be balanced on the overall reaction equation. In an elementary reaction, reactant particles must collide together in order to form products. However, in most reactions, only a small fraction of these collisions will lead to a reaction. A collision between particles that does lead to product formation is called a successful collision. In order for a collision between particles to be successful and form products, the particles must collide with enough energy to break bonds in the reactants. This amount of energy is called the activation energy for the reaction. If the particles collide with too little energy, the particles simply bounce off each other without reacting. No bonds in the reactants get broken, which means no products can then be formed. The particles also have to collide with the correct orientation. This means the particles must hit each other in the right direction in order to form a product. Even when particles collide with the required activation energy, the orientation of collisions still matters. For complex molecules, there's often only one way they can align to react properly. This is why molecules with complicated structures may react slowly even with high-energy collisions at high temperatures. Only a small fraction of collisions between particles have enough energy and the correct alignment. This is why reaction rates are usually much slower than the total number of collisions per second for given particles. A Maxwell-Boltzmann distribution curve describes the distribution of particle energies at a given temperature. This distribution can be used to visualize the fraction of collisions with sufficient energy that lead to a reaction in the mixture, and also how that fraction depends on temperature. The highest peak on the curve shows the most probable energy that molecules have. If activation energy is plotted on the x-axis, only molecules with energy greater than this value can react when they collide, meaning we can see that only a small fraction of the molecules in the system at any one time have enough energy to react together successfully. Increasing the temperature shifts the curve to the right and lowers the peak, meaning more molecules have energy greater than or equal to activation energy. The total number of molecules, however, stays the same, so the area under the curve is unchanged. The area under the curve is proportional to the total number of molecules in the system. Exam tip here: make sure you are able to describe how the Maxwell-Boltzmann distribution changes with temperature. A higher temperature shifts the peak to the right and flattens it. This increases the proportion of particles with the required activation energy. Remember to make sure that you don't change the area under the curve when you change its shape. because this is proportional to the number of particles in the system, and changing the temperature of the system doesn't change the number of particles, meaning the area under the curve must stay the same. A higher temperature means particles collide with more energy, meaning every second there is a greater frequency of successful collisions, increasing the reaction rate. A reaction energy profile is a graph that shows how the potential energy of reactants change as they turn into products. The x-axis shows the reaction coordinates, so up halfway from reactants to products, and the y-axis shows the potential energy of the system. When a reaction occurs, reactants don't simply instantly turn into new products. They have to change. Bonds in the reactants get broken before new bonds in the products can be formed. As a result, the energy of the reactants changes as they get converted into products. The highest energy that they reach is called the transition state. It's a bit like imagining a ball being thrown up in the air. For an incredibly tiny amount of time, the ball will actually be stationary at its highest point in the air. This is a bit like the transition state in a reaction. It doesn't exist for any meaningful length of time, but it represents the highest energy reached by the reactants as they get converted into products. The activation energy for the forward direction in a reaction can be seen on a reaction profile diagram as the difference in energy between the reactants and the highest point on the curve, the transition state. The activation energy for the reverse direction would be the difference in energy between the product to transition state. As mentioned in the previous chapter, not all collisions between particles lead to product formation. Only collisions that occur with sufficient energy, the activation energy, and the correct orientation. Increase in temperature means more particles have enough energy to overcome the activation energy barrier, increasing the reaction rate. Even small increases in temperature can greatly speed up reactions. And this is explained by something called the Arrhenius equation, which shows that rate constant K equals Arrhenius constant A multiplied by e to the power minus Ea over RT. Although it can look quite confusing at first, what the Arrhenius equation really shows us is how the rate of an elementary reaction is dependent upon temperature. Because the equation includes the exponential term e to the minus Ea over RT, as temperature increases, K increases by a much greater factor. An exponential relationship. This is why small changes in temperature lead to a large change in reaction rate. Because remember, using rate laws, rate of a reaction equals rate constant K multiplied by the concentration of reactants raised to their powers. So if the rate constant becomes larger, the rate of reaction also becomes larger. Note that no calculations on the Arrhenius equation will be included in your final exam. However, you do need to be able to explain why small changes in temperature lead to a large increase in reaction rate, and this is explained by the Arrhenius equation. Many chemical reactions don't just happen in one simple step. They occur through a sequence of elementary steps. Each step involves the breaking or forming of a small number of bonds. The overall reaction is the sum of all the elementary steps that occur, and how these steps link together is referred to as the reaction mechanism. Reaction mechanisms have several components: the reactants, an intermediate, and product. The reactants are the species present at the start of the reaction. The intermediates are molecules that are formed in one step and then used up in another step. They don't appear in the overall reaction equation, and products are the substances that are formed at the end of the reaction. Catalysts are substances that appear in one step but are regenerated by the end of the reaction, so they don't appear in the overall balanced reaction equation. Exam tip here: make sure you understand the difference between intermediates and catalysts. Intermediates are formed and then used up in the reaction mechanism. Catalysts are used and then reformed by the end of the reaction. So catalysts are present at the start and at the end. Intermediates aren't present at the start and they aren't present at the end. They're only made and used up during the reaction. All elementary steps must add up to the overall balanced chemical equation. The mechanism should be consistent with experimental observations, and especially the rate law and any detected intermediates. In a multi-step reaction, not all steps occur at the same rate. The step that is the slowest is called the rate limiting step, also called the rate determining step. And it is this step that determines how fast the overall reaction proceeds. It doesn't matter how quickly the other steps occur, it is the rate of this slowest step that will determine the overall rate of the reaction. As a result, it is the slowest elementary step in a mechanism that determines the rate equation. A species must appear only in the rate law if it is part of or directly influences the rate limiting step. This hopefully makes sense because the rate law shows us how the rate of a reaction is dependent upon the concentration of reactants involved. Well, if the fast steps in a reaction mechanism have no impact on the rate of reaction, then the concentrations of reactants involved in those steps don't really matter. But the concentration of reactants involved in the slow step will matter, and this is why the rate law concerns the rate limiting step. Mechanisms can only be proposed using experimental data. Now, the rate law of an elementary step, so a single collision event between particles, can be written directly from the balanced equation for that step. This is really useful because it enables us to determine rate laws for individual steps within a reaction mechanism. For example, if a reaction A plus B plus C goes to form D plus E, has a rate law of rate equals rate constant K multiplied by concentration of A multiplied by concentration of B, this tells us the reaction must occur in 2 or more steps, because the concentration of C isn't included in the rate law, so therefore isn't involved in the rate limiting step. We could propose a 2-step mechanism. The first step being A plus B goes to form an intermediate, and then this intermediate reacts with C to produce our final product, D plus E. Well, the rate law for the first step here would be rate equals rate constant K multiplied by the concentration of A multiplied by the concentration of B. C isn't included because it isn't involved in this particular step. As we know, the rate law overall is rate equals rate constant K multiplied by concentration of A multiplied by concentration of B, this proposed mechanism would be consistent with the kinetic data and the balanced reaction equation. Note, however, that it is still just a prediction. We don't know for certain that this is what happens, it's just this proposed mechanism matches the data we've been provided and the balanced reaction equation. Not all reaction mechanisms start with the rate limiting step. In some cases, the first step is fast and reversible before the slower rate-limiting step occurs. This means the fast step quickly reaches a pre-equilibrium before the slower step. In other words, the fast initial step establishes a dynamic equilibrium between the intermediates and reactants. The slow second step, however, still determines the overall reaction rate. To write the rate law, we can use something called a pre-equilibrium approximation. We express the intermediate concentration using the fast step's equilibrium expression, and we substitute this into the slow step's rate law. This method is closely related to something called the steady state assumption, where the concentration of intermediates is assumed to remain relatively constant throughout the reaction. For example, the overall reaction 2NO plus O2 goes to form 2NO2 has an experimental rate law of rate equals rate constant K multiplied by the concentration of NO squared multiplied by the concentration of O2. Now suppose we have a proposed mechanism of a fast first step of NO plus NO goes to form N2O2 intermediate, and then a second slow step of N2O2 plus O2 goes to form 2NO2. Now, a rate law for the second slow step would be rate equals a constant K multiplied by the concentration of the intermediate, N2O2, multiplied by the concentration of O2. Now, the problem is the intermediate here, N2O2, isn't a reactant, so we can't include it in the overall rate law. However, the concentration of the intermediate, N2O2, is going to be based on the equilibrium between the NO reactants at the start. Now this becomes a bit more clearer when we look at equilibrium in chapter 7, but what this really means is that rather than have the concentration of the intermediate in the rate law, what we can do is substitute in the concentration of that from the equilibrium expression for the fast step. Don't worry if this seems a little bit complicated. The really important thing for you to understand is that if the first elementary step in a mechanism isn't rate limiting, so it's fast and reversible, we have to use approximations to determine the overall rate law expression. As we saw in chapter 5.6, a reaction energy profile is a graph that shows how the potential energy of a chemical system changes as reactants get turned into products. The x-axis represents the reaction pathway, the progress of the reaction, and the y-axis represents the potential energy of the system. For a multi-step mechanism, the profile has multiple humps or peaks, each corresponding to a particular elementary step. Each peak on the reaction profile is a transition state where bonds are being broken and formed, and each valley between the peaks is a reaction intermediate, a temporary species formed between the steps. The tallest peak in a multi-step reaction pathway usually corresponds to the step with the highest activation energy barrier, so this will be the slowest step and controls the overall reaction rate. Exam tip here. Always count the number of peaks in an energy profile diagram to determine how many steps are in the mechanism. The tallest peak usually corresponds to the slowest rate-limiting step, since the activation energy barrier is greatest to produce this transition state. A catalyst is a substance that speeds up a chemical reaction without being permanently changed or consumed. Catalysts work by providing a new reaction pathway that has a lower activation energy barrier than the uncatalyzed pathway. This increases the frequency of effective or successful collisions between reacting particles and makes the reaction proceed faster. Catalysts can work in many different ways, but they usually introduce a new elementary step in a reaction mechanism, and this introduced step involves a new temporary intermediate that includes the catalyst. The overall net concentration of the catalyst remains constant throughout the reaction. The catalyst is often used up in an early step but regenerated in a later one, meaning overall there's no change in net concentration of the catalyst. The rate-limiting step is altered to have a lower activation energy pathway. Reactants bind to the catalyst or interact with it in such a way that causes this decrease in activation energy. The catalyst may help orientate the reactants in a particular way or stabilize a high-energy transition state. Exam tip here: if you're trying to identify a catalyst in a reaction, always look for a reactant that gets used up in one step and produced as a product in a later step. Unlike an intermediate, a catalyst will be present at the start of a reaction and at the end, which is why it isn't included in an overall reaction equation. An intermediate isn't present at the start of a reaction, it is produced during the reaction and then gets used up before the end of the reaction. Catalysis refers to a reaction where a catalyst is being used or a reaction is catalyzed. There are several examples you need to be comfortable with for AP Chemistry. Enzyme catalysis is where enzymes are used. Enzymes are biological catalysts made up of proteins that have active sites. The active sites have complementary shapes that a substrate, biological reactant, can bind to. The binding reduces the activation energy barrier for the overall reaction, allowing it to occur at lower temperatures. Enzyme catalysis is essential for nearly all biological processes. Acid-base catalysis occurs when a reactant gains or loses a proton, a H+ ion, to form a new intermediate. This allows the reaction to proceed through new elementary steps. For example, the decomposition of hydrogen peroxide. The overall reaction is 2H2O2 goes to form 2H2O plus O2, and a H+ catalyst is used. The H2O2 and gains a H+ ion to form H3O2+ in the first step, and then this unstable H3O2+ intermediate breaks down into water and an oxygen molecule. H3O2+ goes to form H2O plus O2 plus H+. Note here that the H+ ion is regenerated at the end, meaning we can consider it to be a catalyst. So the overall reaction would be 2H2O2 goes to form 2H2O plus O2. Surface catalysis, which is an example of heterogeneous catalysis, occurs on a solid surface, often a metal. Reactants adsorb onto the surface, where bond breaking and bond making occurs. A new set of intermediates is formed on the surface of the catalyst before the products diffuse away from the surface. Note it's also referred to as heterogeneous catalysis because the reactants are in a different phase to the solid catalyst, usually gaseous or aqueous reactants. The energy profile for a catalyzed reaction will have a lower overall energy barrier, a smaller activation energy. However, it will show the same energy difference between reactants and products overall, because catalysts don't change the thermodynamics of a reaction, meaning they don't change the overall energies of reactants and products. only the kinetics, so how quickly the reaction happens. So the overall difference in energy between reactants to products will always be the same regardless of whether a catalyst is used. The only difference is the activation energy in the reaction profile diagram.